This lesson deals with a common source amplifier. You can find these notes in the ECE302 ebook in Chapter 5, starting on page 25. What's shown here is a schematic for a common source amplifier using a MOSFET transistor, where for the transistor the threshold voltage is 2 volts, K is 1 milliamp per volt squared, and my input voltage source is 100 millivolts sine of omega t. We have 2 coupling capacitors, coupling the input signal to the amplifier and coupling the amplifier to the load, and then also a bypass capacitor. I've given the values of the capacitors in this particular amplifier, but I'll show you in Chapter 10 how to calculate them. We'll do our 4-step algorithm, the first of which is to find the DC operating point, so we're going to replace every element in the circuit by its DC model. The average value of this voltage source is 0, and that would be the equivalent DC value. Capacitor looks like an open circuit, and an open circuit. Let's just redraw the schematic with those things done. Here's my short for the input, open for that capacitor, likewise in this one too. What about the model for the transistor? Well, we're assuming that we're in the saturation region. This is where it can amplify. Here's where the gate is, and here's where the source is, but there's just an open circuit there. That'll be our gate source voltage at the Q point. And then between the drain and the source, we have the value of K times the quantity gate source minus the threshold squared, but K is equal to 1 milliamp per volt squared, and the threshold was equal to 2. Let's redraw this and begin our analysis. In redrawing the circuit, let me draw the power supply twice. And by doing that, I break the circuit into loops that I can analyze a little bit easier. We're going to solve for the gate source voltage and then eventually the drain current. But to do that, I need to find this node voltage and this node voltage. This is just a simple voltage divider with 1 million ohms and 3 million ohms. 1 mega over 1 mega plus 3 mega times the 20 volts is a quarter of the power supply, or 5 volts. The source voltage is going to be the resistor that's here times the current that's flowing through it. The gate source voltage is the difference of those two. We just found the gate to be 5 volts, and then we've got a current going in a 2.7K resistor whose value is 1 milli times the quantity V sub GS at the Q point minus 2 squared. Let's multiply that out. At 5, the K and the milli cancel. I'm going to square this so I get the gate source squared. Inner product times 2, so minus 4, and then a minus 2 squared, which is 4. Multiply the 2.7 out. I get a minus 2.7 times the gate source squared. 2 minus signs become a plus. 2.7 times 4 is 10.8. And I got the same number again, but with a minus sign. I'm on the other side of the equation. I get a plus 2.7 times the gate source squared. I have 10.8 times the gate source voltage on the other side of the equation. I have a 1 times this. I'm bringing this over as a minus 10.8, so I get a minus 9.8. And then these two together gives me a minus 5.8 on the other side of the equation, a plus 5.8. And use the quadratic formula to find the roots of this equation. And since this has a unique answer, one of these has to be inconsistent. I take this equation where I've got a times x squared plus bx plus c, and then the value of x is equal to minus b plus or minus b squared minus 4 times a times c divided by 2 times a. This gives me 9.8 plus or minus 5.779 divided by 5.4. When I add the two quantities, I get 2.885, and when I subtract them, 0.745. The threshold voltage is 2, and this is less than threshold, so that's inconsistent with being in the saturation region. In fact, it would be cut off. So we're going to throw this one away. We have a gate source voltage equal to 2.885. Calculating the drain current at the Q point, that's going to be K times the quantity gate source voltage minus threshold squared, 1 milliamp per volt squared, 2.885, and a threshold voltage of 2. Gives me 783 microamps. Now I need to calculate the gate to drain voltage to see whether I am actually in the current saturation region. Let's go back to the schematic at the top of page 26 and find this voltage here. I've got a current in here. That's going to give me a drop in this direction. This node voltage is equal to minus I sub d times 4.7K plus 20. If I go around the loop this way, I'd have to know what the drain source voltage is. I can solve for it, but I don't know what it is. So I'll go around the loop this way. Here's my gate voltage of 5. My drain is minus IDQ times 4.7K plus 20. The value of this was 783 microamps. I get 5. The two minuses become a plus, and that times the 4.7K is 3.68, and then a minus 20. That's a minus 11.3. The gate source voltage is equal to 2.885. That's greater than the threshold voltage of 2. And the gate to drain is a minus 11.3, which is less than 2. Therefore, our assumption checks. Next step in our algorithm is to calculate the AC parameters. There's just one here in our model, and that's the value of GM. That's 2 times the square root of K times IDQ. K was 1 milliamp per volt squared. I sub dq was 783 microamps, and the square root of that times 2 is 1.77 millimos. Step 3 is to find the AC results in the mid-band frequency range. We're assuming the frequency is high enough that the capacitors in the circuit look like short circuits. Let's go back to the schematic on page 25. Let's redraw it again and replace the capacitors C1, C2, and C sub S with a short circuit. An AC voltage source is an AC voltage source, but a battery looks like a short circuit for AC, so we're just going to short that. And then between the gate and the source and the drain and the source, we have an AC model. We have an open circuit here, and then between the drain and the source, we have a current source again that's controlled by a voltage, but now it's GM times VGS. We have a lot of ground symbols here, and let's just redraw this, and then we'll do the analysis. In redrawing this with a common ground, we have that the ground is actually equal to the source of our transistor, and between the gate and ground, we have this R2. We also have R1 back to ground, and then we have this grounded. And then between here and ground, we have this resistor of R sub L, but also R sub D, and the controlled source in parallel with that. Let's see what that looks like on the next page. Here's our common source. Here's our input, hooked up through a 100K resistor to R1 and R2, which are connected in parallel because of the shorts, and then these three in parallel. What's common between the input and the output is the source of the MOSFET transistor as an AC model. Let's find our 5 parameters of the amplifier. First one is the voltage gain. That's V out over V in. V in is measured here on the other side of the Thevenin equivalent circuit of the source. So what's the output voltage? It's going to be this current flowing into these two in parallel. 4.7K in parallel with 10K times the current in this direction, which is a minus 1.77 milli times VGS. This parallel combination is 3.197K. It's a little bit smaller than the smaller of the two. You multiply these two, you get a minus 5.66. But the gate source voltage, between here and here, is also the input voltage. Now I have V out over V in as a minus 5.66. Let's find the input impedance. Well, we've got our two resistors in parallel. Let's be 3 megohms in parallel with 1 megohm, and that's 750K. Very large input resistance. We don't have an RPi to deal with the FETs. Next is our current gain, and that's going to be our voltage gain times Z in over R sub L. Voltage gain was minus 5.66. Z in was 750K and R sub L was 10K. We have a very large current gain. Notice that the voltage gain and current gain always have the same sign because of this relationship. So we will get a positive power gain. Our power gain is the product of the voltage and current gain. That's 2,403. A very large number because of that large current gain. And lastly, what's the output impedance? Set all the independent sources equal to 0, take the load off, and look back into it. Because there's no connection between here and here, if we were to apply a voltage, there's no way for voltage to get back here. That's going to make this voltage equal to 0, like we saw for the common-emitter amplifier. So all we see is the resistance looking back of 4.7K. So lastly is our assumption of small signal valid. We have to find the gate to source voltage. Let me not scroll back, but just simply look at this drawing here. You have a voltage source here of V sub S, and we're going to find the gate source voltage, which is a voltage divider of these two resistances with R sub S1, which is again our Zn over R sub S1 plus Zn. We got 750K and 100K, voltage dividing down to 100 millivolts. That gives me 88 millivolts sine omega t. And the sign, of course, can be positive or negative, but its largest value is when this is equal to 1. That has to be less than twice the quantity of the gate source voltage at the Q point minus the threshold. That was our test for small signal. That turns out to be 1.77 volts, and of course that's much bigger than 88 millivolts. So yes, it was a correct assumption. And lastly, we're going to add the AC and DC results. For amplifiers, we're going to block the DC so we don't push out a DC signal into a speaker eventually. And all I've got then is just the voltage gain times the gate source voltage, which we found to be up here to be 88 millivolts and the sine of omega t with a gain of minus 5.66. That gives me an output voltage of about a half a volt times the sine of omega t. Let's do a comparison of this common source amplifier with the common emitter amplifier we did previously. We saw in this last example that the gain in magnitude is 5.66 compared to the common emitter amplifier of 105.7 in magnitude. They had about the same biasing current. So was this a fluke or does this always happen? Well, let me take a look at the following. Let's take our model for the BJT low frequency and let's convert it to something similar to what we had for the MOSFET. The voltage V pi is equal to IB times R pi, and this collector current is just a controlled source of beta FIB. But if we substitute in here that I sub B is V pi over R pi, bring the R pi over here, we have that the collector current is something times the voltage across the base emitter. And that would be equal to beta F over R pi, and we can define that to being a transconductance, just like we did for the MOSFET. GM would be beta F over R pi, But our pi is eta v sub t over I sub b. Bring it up in the numerator. I got beta FIB at the Q point over eta f v sub t. And of course, this is my collector current at the Q point. So I'm relating GM to the biasing current of my transistor. My model will be the same for our pi here, but now I'm going to have a controlled source that depends on the voltage here and not the current, but it does indirectly with these equations. For the FETs, we have the GM is 2 square root of k times IDQ, and of course the GM here has got an I sub CQ here, so we're proportional to I sub D and I sub C at the Q point, but we have a square root here. This is going to make GM much, much smaller, and that's why the gain went down. So we'll always see that for the same currents, the BJT will have a greater gain. When we do IC design, we have to take this into account that the structures we use for biasing a BJT will not work well for having gain with a MOSFET or a JFET amplifier. And this is the analysis of a common source amplifier.